In this second module of Chapter 2 on life tables, Module 2.2, I will cover computational methods for the 5 basic parameters of the life table. But before I go into the actual life table construction, I will first lay out and briefly describe the different life table categories for a perspective on the life table we are about to construct. Life tables are classified according to 3 categories. The first is by data type, including longitudinal, where data are gathered on a true birth cohort, or by cross-sectional data, where a synthetic cohort is used. This is used to construct a period life table, a method I will cover in a subsequent module. The second life table category involves age and includes either complete, in which data on all ages is included, versus abridged, where ages are lumped, such as 0 to 5, 6 to 10, and so forth. The third category is by decrement, in which a single decrement life table lumps all causes of death, whereas a multiple decrement life table disaggregates death by cause. Thus, the life table I will construct in this module is a complete, single decrement cohort life table. So, cohort life table construction. A complete single decrement cohort life table is constructed by starting with a group of same-aged individuals and recording the number of deaths in the group at each point in time until all individuals have died. The raw data is organized in columns, starting with the number alive at the beginning of each age interval. This and other information is arranged in a table with 7 columns, as specified here, with rows for age classes. An example of a complete cohort life table is given in the table for the fruit fly Drosophila melanogaster. By convention, a cohort life table for Drosophila begins at eclosion, that is adult birth, when a new adult emerges from the pupal stage. This life table information that I present here is based on unpublished data from biogerontologist Robert Arking, in which survival of 666 adult flies was monitored and recorded and arranged according to their survival by age. Column 1, Age Class X. This is the age index and designates the exact age that an interval begins, with a unit of days for Drosophila. Age class X refers to the interval from exact age X to exact age X plus 1. That is, the age class 0 specifies the interval from age 0 to age 1. Column 2, Number alive at age X, denoted NX. The data in this column contains the number of individuals alive at age X. For example, from this table, the number at age 0 we start with at 666, and the number at age 20 equal 585, which in words means that the cohort started at age 0 with 666 individuals, and by age 20 there were 585 individuals remaining. Column 3, Cohort Survival to Age X, LX. The first fraction in this column, L0, is the radix, and each successive number represents the fraction of survivors at the exact age X from the cohort of size L0, that is normalized to 1.0. For example, from this table, survival to age 10 days, denoted L10, is computed as the number surviving to age 10 divided by the original number, which equals 656 divided by 666, or 0.9851. Likewise, L25 is computed as 516 individuals out of 666 survived to age 25, or 0.7741. In words, the fraction of the initial cohort that survives to age 10 and 25 days are 0.9851 and 0.7741 respectively. Fewer than 2% were dead after 10 days, but nearly a quarter were dead after 15 days. Column 4, Period Survival PX. This parameter is defined as the proportion of those alive at age X that survive through the interval X to X plus 1. For example, P10 equals the fraction of the cohort that survived to age 11. L11 divided by the fraction that survived to age 10. L10. Thus, 0.9806 divided by 0.9851 equals 0.9954. Similarly, P25 is the dividend of L26 and L25, which yields a value of 0.9724. Thus, the probability of a 10-day-old female surviving to age 11 is 0.9954. 15 days later, the probability of this fly, now 25 days old, surviving for one more day is reduced to 0.9724, or by over 2%. Although this difference in one-day survival probability appears small, when re-expressed as a probability of dying, the proportional difference is relatively large, as will be seen with the next parameter, QX. So column 5, period mortality, QX. This parameter is defined as the probability of individuals alive at age X dying in the interval X to X plus 1. For example, the fraction that die in the interval 10 to 11 days equals Q10 equals 1 minus the fraction that survive, as shown in the right-hand ratio of L11 and L10, and as computed in column 4. This computation yields a value of 0.0046. A similar computation for Q25 on the right yields a value of 0.0276. Thus, the probability of a 10-day-old female dying before she is age 11 days is 0.0046. 15 days later, the probability of this fly, now 25 days old, dying the next day is increased to 0.0276, essentially a six-fold increase. Column 6, frequency distribution of deaths, dx. This column contains the fraction of the original cohort, L0, that die within the age interval x to x plus 1. The dx column thus represents the frequency distribution of deaths in the cohort, and the sum dx across all ages is unity, or 1.0. The fraction of the newborn cohort that die in the intervals 10 to 11 days and 25 to 26 days, denoted T10 and D25 respectively. The Lx values substituted into the dx formula yields the value shown here. In words, a new adult fly has a likelihood of dying in the intervals 10 to 11 days and 25 to 26 days of 0.0045 and 0.0214 respectively. Column 7, expectational life at age X, EX. This gives the average remaining lifetime for an individual fly who survives to the beginning of the indicated age interval. For example, plugging in and summing the Lx values from age 11 to the end of life, shown in the second expression, and dividing this by the value of L1 and adding 0.5 to this dividend yields 29.5 days. In words, the average 10-day-old fly has a 29.5 days of life remaining. Life table parameter visualization. Each parameter of the life table reveals different information from the same basic data. For example, the survival curve Lx shown here shows a gentle slope at younger ages, followed by a moderately rapid drop in survival at the middle and late ages. The fine details of daily survival and mortality are difficult to discern from the survival curve, but they are clear from the mortality curve. The age-specific mortality QX shows a low risk of death at young ages, followed by the ever-increasing risk of death through the remaining life course. Although the death distribution can be inferred from the Lx schedule, the Dx schedule shows this distribution directly and clearly and highlights the patterns, shows that the vast majority of deaths occur in the 50-day period between 15 and 65 days. The life expectancy at age X, EX, is a standalone metric that graphically shows the actuarial outcome of present and future mortality at each age. Life expectancy EX cannot be inferred directly from any of the other parameters. This completes Module 2.2. In the next module, I will cover what is referred to as life table censoring, in which situations arise where the number of individuals at risk at some or all ages needs to be adjusted.